Okay, so when it comes to practice, there's a bunch of correlations you can use. Sorry, let me flip the coloring here. Oof, okay. There's a bunch of correlations that exist for different geometries. So you might have a horizontal plate, you might have a vertical plate, you might have a tilted plate. In a tilted plate situation, the heated surface might be down, it might be up, you might have a sphere, cylinder, or so on. So all these different situations, there are correlations that exist for them. There's maybe some classification considerations that we want to go through. So let me just write those down first. So again, you're going to maybe have laminar versus turbulent. Like, believe it or not, you could have turbulent natural convection. You have the geometry of the object. You have the direction of gravity. You have the consideration of whether Ts is greater than T infinity or whether Ts is less than T infinity. So that's a new one, right? Oh, so is direction of gravity. But if you have the situation reversed, it actually changes the correlation sometimes. You could have internal and external. You could have different boundary conditions types, so like constant flux versus constant temperature, same as before. So those are the things that you're going to want to use to maybe decide which correlation to use. The reality is, like, if you have the right geometry and the right, let's say, laminar versus turbulent, you're kind of limited on what's available. Like, there's not a huge amount of stuff out there for free convection, but at least these are the things you want to look for, characteristic-wise. Okay. All right. So free convection correlation. Let's just go through an example for a vertical plate, and you'll kind of see what it looks like in that situation. So for a vertical plate, this is the correlation that's given. This is a correlation in terms of the average Nusselt number for a vertical plate. We have a Nusselt number, this relationship. Note what it depends on. It depends on the Rayleigh number. It depends on the Prandtl number. So you're going to have to figure out how to compute those non-dimensional quantities, as is shown on the right, in order to decide how to evaluate this correlation. One other thing to point out is that the critical Rayleigh number is something like so because it's basically the Reynolds number squared times the Prandtl number, you're going to have a larger criteria for the transition. So this is typically where you see that transition happening to turbulent flow. So this would be to turbulent. Okay, what does the boundary layer look like? You still have a boundary layer that develops for these things. So what does that look like? Let's sketch it out. So here's my vertical plate. I have a boundary layer. Let's say the vertical plate starts down here. My boundary layer grows like this, just like it would before. So this is, let's call it delta M. And then let's say that this is Ts, and then this is T infinity. So what does the velocity profile look like in this boundary layer? Well, we have kind of a different situation, right? Now we don't have this free stream happening out here. Like out at the boundary layer, it's not like the air is moving, right? This is stagnant air. It's just sitting there. We also then have at the surface a no-slip condition. So as opposed to having this like parabolic solution, we actually have two places where we have to force the velocity to be zero. So that would look something like, let's say, at the wall here. Let's just kind of sketch what this looks like. The velocity profile might be zero, and then it's zero out here as well, and it might look something like this. So this is my velocity profile on the boundary layer. It's a little different. This would be, let me just label it as u as a function of, let's call this coordinate here y, and then this coordinate here x. So this is u as a function of y. Okay, so that's generally what it looks like. With the last few minutes, so what I want to do is just kind of go through some other examples. These I mostly have written out the notes, but there's maybe a few things to add. So if we have free convection on a horizontal plate, it's basically the same thing, but you have these additional parameters you want to evaluate. So we would go in, we'd identify, this is my Nusselt number correlation. For flat plate, it calls for this C laminar, C turbulent. So now I have to decide, okay, is it laminar or turbulent? I'm compute the Rayleigh number. Which is it? And then I'm going to choose based on those two things. So if it's laminar, then I compute C laminar. If it's turbulent, I compute C turbulent. Note there's like different considerations for these things. What would this look like in practice? I guess it would look something like the plate's down here, and maybe you have like these vertical convection lines that sort of meet at some point. This again is sort of how our atmosphere works. You get heating on the ground. You get this vertical, like these tunnels sort of velocity, high velocity going up. So this would be an example. And then we have the question of, okay, I have a laminar and I have a turbulent. How might I combine those? So I have two different correlations, one for laminar, one for turbulent. I don't want it to be the case that if I were to like hit my transition, that all of a sudden I have like a completely different value. Because when you're solving the problem, it's like tough to deal with that numerically. So there's a way that people typically deal with this, and it's by mixing the two models together with a power. What I mean is, okay, so let's say I want to compute the Nusselt average. I can do that if I use both correlations. So I would say Nusselt laminar plus Nusselt turbulent. And I take each of them and raise them to some power. So I'm going to say, let's take this to the 10th power and the 10th power. And then I take the entire thing and take it to the minus 10th power. Right? Or maybe let's write it this way, 1 over 10. Either one is fine. Okay, so what have I done? Well, I've basically said whichever one of these is bigger is going to completely dominate the solution. But at the point where they're about the same, they actually then have a smooth transition from one to the other. In this case, like it's a very, very fast transition because the 10th power really forces that. But you don't have to use 10. Like you can use something else. For this particular correlation, they happen to use 10, which is why I'm giving this example. But on the next slide, let me just show you kind of what happens in other situations. So let's say we have, just in general, we want to combine two different like correlations together. So let's say we have H bar combined of like a forced convection, H forced, and H free. All right, so let me stop a second. So what I'm saying here is, let's imagine that I have a wall, and this wall is hot, the air is cooler. There's natural convection that's occurring. Now I turn a fan on over here, and I've got both the natural convection that's occurring and also forced convection that's against the wall. Both of those are potentially important. So we have to account for both of them. So I'm taking my forced convection and free convection, and I'm going to add them together in some way. Well, it turns out that, again, if the forced is much more significant than the free convection, that one dominates. And vice versa if it's the other way around. But it's not quite as severe as that 10th power. So what I can do here is let's take this to some, let's see, what did I do? Take it to some power m, and then take the summation of that to the 1 over m. So normally we say m is about 3 is pretty normal. So where there's one that's much larger, it drives the value. But in the mixing, or in the intermediate region, there's, yeah, both can be important. Okay, so let's see. This is for a situation where both the forced convection and the free convection are acting in the same direction. What happens if, let's say, you have natural convection occurring this way, and for some reason I put a fan up there and blow downward? Okay, so what would happen then? Well, it's sort of the same, it's just a little bit more messy, but it looks like this. So it'd be H bar combined is equal to, now let's take the max like the maximum value of either h bar forced or h bar free. Take that to the m power, and then take the minimum of those two values, h bar forced, h bar free. Take that to the m power, and then take all of that to the 1 over m power. So this is a situation where you'd now be able to account for one counteracting the other. It's a little weird, but I guess you could think about it. Okay, last slide, and then I think we'll kind of wrap up here, is the internal free convection. So what I'm showing here, it's a little hard. I could flip it, but I don't really feel like it. So what I'm showing here is a heat sink. Okay, if you go over to the any of the power electronics labs over in the EC department, or this happens to be in my lab, this is a heat sink that's on the back of some testing equipment. So the computer, the CPU itself is sitting there getting really, really hot. It's a big thing. And we need to reject the heat. So we have this big copper heat sink. It's mounted on the back. And then what happens is it just sits there, and the flow kind of naturally convects up through it, and it cools the system. So it's like important in this situation to understand it. But what you actually get is like the boundary layers intersecting between these nice little fins. So you have this correlation here that kind of covers this. Now we have internal free convection, right? This can be a thing. You go through the process of computing it this way, all right? There's one more slide if you want to look at it. It's enclosure. There's an enclosure option as well, but we'll leave it there. All right, thanks everyone.